Thank you so much, Marie-Manuel. Thank you to the Scientific Committee and local organisers for giving me a chance to speak. This is a talk that has two different halves in a way. On the one hand, it's a survey of magnitude homology. On the other hand, it's about joint work with Adriano Donia Mateo, who is... where is he? Where is he? Somewhere else. Right. Okay, and if you want to follow along, you can find a link to these slides at the top of my webpage. Right. Okay, so let me give you a preview of where we're going to get to. Magnitude homology is a homology theory of enriched categories, and in particular, it provides a homology theory of metric spaces. So I'll talk about both those levels of generality in some generality. And then I'll get to this, this ongoing joint work, which is about when two subsets of Euclidean space have the same magnitude homology. So magnitude homology is not the same as topological homology. And I'll define all the terms in the status of that theorem. First of all, what is magnitude homology? Well, it was first defined in the generality of graphs by Richard Hepworth and Simon Woollerton, who is there, and then generalized by, well, principally Mike Sean, but also me, to enriched categories. Right, so we'll warm up with something classical, which is the homology of an ordinary category, I mean a small category here. If you start with a category, then you get a chain complex. What you do is the nth chain group is free on the set of paths of length n. And I've written that in a certain convenient way on the slide. So that the part after the z is the set of paths of length n, and then you form the free abelian group on that, and then you take a co-correct. And this has a differential, which, like many differentials, is an alternating sum. And the ith d, the di, usually it composes. So it composes at xi unless I is either 0 or n. And in that case, it just drops off either the first or the last bit of the path. Okay, so that's the differential. You get a chain complex, and you can take its homology. And this homology of a category has all the properties you might imagine, even if you've never encountered it before. As I said, this is something classical. For example, it generalizes the homology of groups seen as one-object categories. And also, if you take the nerve, or classifying space of a category, and you take its homology in the topological sense, that is the same as this homology here. So it does what you'd like it to do. We're interested in extending this definition to enriched categories. So let's have a think about what properties of set we've used here. Well, we've used the fact that set is a monoidal category because look, there's these time signs are as a monoidal structure in the category of sets. We've also used the fact that the unit object of sets is terminal because d0 and dn drop off the last element of the chain of the path. And so what we're fundamentally doing is taking the map to the terminal object when we project. We're projecting out the first or last onset here. We're using the fact that AB is an abelian category in order to do homology. And although it doesn't quite appear in the definition, we're kind of using the fact that abelian groups form a monoidal category. When you actually go a bit further than just stating the definition, you always need the fact that the free abelian group on a product is the tensor product of abelian groups. So we use the fact that AB is monoidal, and we use the fact that the free abelian group functor is a strong monoidal functor. Okay, so those things are all in there. Right, so that suggests a way of extending the definition to monoidal categories, and we do exactly that. There's nothing particularly inspired going on here. So I call this the magnitude homology for reasons that I'm not going to explain unless someone asks me to afterwards. But imitating this set case, the unenriched case, we take some other monoidal category whose unit object is terminal, the so-called semi-Cartesian category, and we take some other monoidal abelian category and some other strong monoidal functor, following sigma. And if we start with a V category, a small V category, now then we define a chain complex in exactly the way you'd imagine from the previous slide. And you define the differential in exactly the way that you would imagine. And you define the homology in exactly the way you'd imagine. So it's just a straight generalization from the setup I told you for unenriched categories. So that's the definition of the magnitude homology of an enriched category. You do have this choice of the abelian category A and of the strong monoidal functor sigma. Right. Now comes one of my favourite moments of the talk. We're going to specialise it to metric spaces. I'm going to use the fact that metric spaces are enriched categories. I take a dramatic pause because I just love explaining this. So Dirk mentioned this yesterday and Isar said rather more about it today, that it was an insight of Lorvier's 50 years ago that any metric space can be seen as an enriched category. Now, most of you know all about this. Some of you, I suspect, do not know this, and so I'm going to spend a minute on it because it'll make your day. It's really it's the best thing. So it's not saying that metric spaces form an enriched category, it's saying that each individual metric space can be seen as an enriched category. The monoidal category you're enriching in is the poset of non-negative reals with the reverse of the usual ordering. So when you view a poset as a category, you know, there's a choice of orientation. So here, the category corresponding to the non-negative reals, there's a map from 4 to 3, but not a map from 3 to 4 for each instance. The monoidal category is addition, and if you have a metric space, then you can see it as a category enriched in this V by saying that the points of your space are the objects of the category. The homs are the distances, right? So hom A, B is meant to be an object of V, in other words, a non-negative real, and that is the distance. And then composition, for example, is meant to be a map from hom AB tends to hom BC to hom AC, and that becomes the assertion that the distance from A to B plus the distance from B to C is greater than or equal to the distance from A to C. It's a triangular homology. So I don't have time to go into it more than that, but it's such a beautiful idea, and yeah, spend some time this afternoon thinking about it, and you'll emerge smiling, I promise you. So there we are. We've got our V. Its unit object 0 is terminal. And therefore we have a hope of doing homology of metric spaces. In order to do that, we have to make these choices. We have to choose an A and a sigma. And it's not so easy to see what you could possibly do there, because think about sigma of 1, for example. So 1 is half plus half, which means that sigma of 1 is sigma of half tensor sigma of half. Right? So whatever sigma of 1 is, it has to have a monoidal square root. If you imagine that A is abelian categories, abelian groups, for example, then you know which abelian groups have a tensor square root. And similarly, sigma of anything has to have a tensor 17th root, and so on. The choice we make is kind of, in some sense, the free possible choice, the universal choice. So we actually take A to be a large power of abelian groups, and it has the convolution tensor product. And sigma is sort of a Unederi type thing, or a Dirac delta type thing, where, well, it does what it says on the screen. So it just tests whether the two real arguments are equal or not in outputs, either Z or 0. So that's, other choices of A and sigma are possible, but like I say, it's not so easy to find any, and this is, in some sense, a universal one. So now, in principle, I told you all the definitions. You could go away and try and calculate the magnitude homology of I don't know, circular radius 3 or something. But I'm going to say a little bit more. I'm going to say what the explicit version of this is. And this is going to be one of those times, you know, people say this in talks, that I'm going to show you a slide with some details in that you don't have to take in, which is a bit of a weird thing to say, but I'm going to show you a slide with some details in that you don't have to take in. But just to kind of show you what it actually means to do this thing. So explicitly, you start with a metric space. You write down the chain complex where the nth chain group is generated by all sequences of n plus 1 points, where the total distance, this plus this plus this, is L. Because there's this L here is the, the L refers to this power up here, right? So I'm putting it as a superscript rather than a subscript, but this Cn of x is not just an abelian group, it's a whole family, uncountable family of abelian groups. So that's how it's defined. For convenience, you can actually pass to a kind of normalized version in a standard homological way. You can ask that the neighboring points are distinct from each other. That makes things a bit more finite and easier. And the differential is, again, an alternating sum, where the only time it's non-trivial is when you've got, on this little path, you've got 2 points between each other, where by between I mean that the triangle inequality is an equality. So that's what it looks like, and you can calculate away, and that's what the magnitude homology is. So, like I say, you don't need to take that in, I just wanted to show you roughly what it looks like. The more important thing to think about is not what the definition is, but what the type is. So I want to emphasize the fact that this is a graded homology theory, a real graded homology theory. So when you take a metric space, X, and you take a natural number n, the nth magnitude homology is not just one abelian group, it's a whole infinite family, an uncountably infinite family of abelian groups with a length parameter, L. And if you know about Kovanov homology, that's a great comparison to keep in your head. Here are some sample results in a kind of survey-ish spirit. One of the first things that was realized was that magnitude homology detects convexity. So if you take a closed subset of Euclidean space, its first magnitude homology is trivial if and only if the set is convex. So this means it's a genuinely geometric theory, not a technical sense. It detects geometric information, not just topological information. So zeroth topological homology detects connectedness, for example, this detects convexity. You can take that thought a bit further. So convexity is about the existence of geodesics. Work of Gomi and others have shown that the multiplicity of geodesics affects the higher magnitude homology. And so another thing along roughly similar lines, ordinary topological topology famously tells you whether holes exist in a space. Magnitude homology, being a metric theory, tells you how big the holes are. So a result of Kaneta and Yoshinaga goes as follows. That's Yoshinaga on the right. I couldn't find a picture of Kaneta or Gomi, so no photos of them. On the left, that's meant to be R2 with a hole in it. The general result is if you take Rn and you put a hole in it of radius R, then just by knowing the magnitude homology groups, or even just by knowing which ones are trivial, which ones aren't, you can recover the radius of the hole in a certain way that doesn't really matter now. Okay, so it gives you this geometric information. Now, that's the end of the little survey of what magnitude homology is for both enriched categories and metric spaces. I'm now going to move on to the theorem that we're leading up to about magnitude homology of closed subsets of Euclidean space, and when two subsets have the same magnitude homology. So the immediate question is, what does it mean to have the same homology? So anyone who's really done any homology of anything will probably have reflected a little bit on this, and this is a general philosophical side about any homology theory of anything at all. So if you say that two things, x and y, have the same homology, you could just, the most crude interpretation of those words is that their homologies are isomorphic in all degrees. And generally that's seen as not a particularly useful thing to look at, that you get too many spaces coinciding. And indeed that's also the case here. So Emily Roth, who is there, demonstrated this by exhibiting two spaces in her thesis that have the same first magnitude homology but different topological homology. And you can in fact find spaces that have the same magnitude homology at all degrees and different topological homology. And so we're not going to interpret it that way. There's another way of looking at it that's seen very often in homological algebra, which is you say two spaces have the same homology if there's a map from the first to the second that induces an isomorphism in homology, and then you have to close under symmetry and so on to make it an equivalence relationship. And that's called quasi-isomorphism. And that's fine, but that's also not what we're going to be doing. We're going to be making it tighter still and asking for the existence of maps back and forth in both directions that, when you pass to homology, become inverse to each other, that become inverse isomorphisms. Yeah, so you could call this like strong quasi-isomorphism or something gruesome like that. I don't know if there's an official name for this, but that's the one that I'm going to be talking about today. So the objects are metric spaces, and the maps are what Lorvier's insight tells you. They're the enriched functors, which are the maps such that the distance between f of A and f of B is less than or equal to the distance from A to B. You go on to several maps. I'll call them distance decreasing. That's decreasing in the non-strict sense. So, the theorem will say that when you take two closed subsets of Euclidean space, they have the same homology in this sense. I'm discarding degree 0 for boring reasons I won't go into. If and only if there's a certain concrete geometric condition that relates x and y. So my next job is to say what that condition is. Right, so here's where it gets quite concrete. Start with a metric space. We can say that 2 points are adjacent if there's nothing in between them. Again, between in the sense of the triangle inequality. So, in other words, whenever you've got a z between x and y, then if the triangle inequality is an equality, then z has to be either this point or that point, x or y. Right? There's nothing between them. And the inner boundary consists of all the points that are adjacent to something. One justification for the name is that if you take a subset of Rn, the inner boundary is a subset of the topological boundary, because if you're in the interior, that means you've got a little ball around you, which means you can't possibly be adjacent to anything, because you've got points closer and closer to you. I'll show you some examples. Here's the definition again. Right, suppose we take an annulus. The points on what you would intuitively call the inner boundary are indeed the points of the inner boundary. Those are the ones that are adjacent to something. As a kind of limiting special case of that, you take a circle, the inner boundary is the whole thing. Similarly, if you take R2 with two disks removed from it, the inner boundary is what you might think. If you take a convex set, the inner boundary is empty, and in fact, for closed subsets of Rn, to be convex is exactly to have empty inner boundary. What next? If you take this C-shaped thing, the inner boundary is the kind of the concavity, the dimple in it. Another kind of irregular shape. The inner boundary is most of the boundary except for the bulgy bits at the end. Right? The bulgy bits at the end, the points on them aren't adjacent to anything. If you draw a straight line from one of those non-inner boundary points to something else, you'll see it crosses the set. A finite set, well, every point in it is adjacent to some other point. This L shape, so this L shape is interesting because the elbow of the L, this point here, is not adjacent to anything. And so the inner boundary is everything except for that elbow point, which demonstrates in particular that the inner boundary doesn't have to be closed. And then finally, here's just a completely irregular shape, and the inner boundary is everything, if I've drawn it right. It's crucial that there's a stalky bit on top and another little bit on the bottom, otherwise that wouldn't be true. Okay, that's the first thing. That's the first of three geometrical things that I need to say. The second one is we're going to pass to the closed convex hull of the inner boundary, which is to say the smallest closed convex set containing the inner boundary, or the intersection of all closed convex sets containing the inner boundary, which I'll draw in yellow. And so we just do this, we do this, we do this. In the case of that convex set, well, we're taking the closed convex hull of the empty set, so it's empty. So we're kind of filling in the dimples, we're filling in the... oh, I've done that wrong. But yeah, that picture is wrong. I should have filled in the dimples there, I apologise. And so, yeah, we just keep taking the closed convex hull of each of those things. And then the final step is to take only the parts of the closed convex hull that are in X. I'll call this the core. So the core of X, drawn in purple, I'll define as the intersection of the closed convex hull with X. So in the case of the annulus, we get the inner boundary again, and similarly for the circle. For this thing that's starting to look like a cassette tape, you get something kind of like a pair of binoculars or something in the middle. And then these ones, so that irregular shape here, that now is correct. So it's everything except for the bulgy bits at the end. And then the last three, the core is actually the whole thing. So we chose the word core because it's an idempotent process. If you take any subset of Euclidean space, it has a core, but if you take the core of the core, you don't get any further. So that's as far as it goes, right? So if you're the core of something, then you're the core of yourself. Okay, great. We're ready for the main theorem. Maybe I'll pause for a moment so you can remember the definition of core before I move to the next slide. This is where the people who do Blackboard talks feel superior.
I mean, here, to define the middle step in this notion of core, you're using the ambient metric space.
That's correct.
Does that work for all embedded metric spaces, or is there something about it being Rn?
Yeah, right. So, thank you. That's a good question. There are many possible degrees of generality. Convexity can be defined in multiple different ways in Rn, and if you try generalizing that to other metric spaces, you immediately find that all those definitions diverge. So you can do some in the context of geodesic spaces or geodetic spaces or spaces with no forecuts or blah, blah, blah. So there are all these different levels of generality, but as we've got more and more specialized, our desire to, or in fact our need to specialize to Rn increased. So yes, so the definition of inner boundary is for an abstract metric space, but this stuff is for closed subsets of Rn. Thank you. Okay, great. So time for the main theorem. Here we go. We take two closed subsets of Rn, and the following are equivalent. First of all, that they are homology equivalent in the way I've been talking about. You might be expecting from my previews that there are going to be two conditions here. There are actually going to be three. So that I'm sneaking in a further one. The only difference between 1 and 2 is that in 1 I said for all n, and in 2 I said for some n. And it turns out these things are equivalent. And then the final condition is that the core of x and the core of y are isometric, the distance-preserving isomorphism. So 1 implies 2 is trivial. 2 implies 3 is saying, for instance, that if they're homology equivalent, if you have maps inducing a homology equivalence in degree 17, then the cores are isometric. And 3 implies 1 is saying if the cores are isometric, then you have maps inducing homology isomorphism in all degrees. I'll say almost nothing about the proof, except that it leans heavily on a theorem of Kaneta and Yoshinaga, and it also uses what, I think for us at least, was a quite substantial amount of convex geometry that we had to create. Well, some of it may exist in the literature, but we couldn't find it. Maybe metric geometry would be a better way of putting it. So in particular, every set has the same magnitude homology as its core. And if you'll let me, I'll just briefly flash back to these examples. So for instance, if we look at this kind of what I think was a jellyfish, then trimming off these bulgy bits doesn't change the magnitude homology. If you look at this C-shaped one again, the magnitude homology of the whole thing is the same as the magnitude homology of the purple bit. And similarly, this one here, remember this is meant to be the whole of R2 with the disks removed. You can shrink it down, but you can't shrink it down all the way. You have to keep this purple bit, the core, in the middle if you don't want to change the magnitude homology. So that's the theorem. As a summary of everything I've said, there is a homology theory, magnitude homology of enriched categories. You can apply that in particular to metric spaces. And in particular, again, if you apply it to closed subsets of the Euclidean space, then two sets have the same homology in this sense, if and only if some concrete geometric condition holds. So that's references. I maintain a web page with all the works on magnitude that I know about, which you can easily find. And there's a section of that webpage on magnitude homology, and every paper I've mentioned is listed there if you want to find it. Thank you very much indeed for listening.
George?
For ordinary homology, what you show us like this is treated by a homotopy. Do you have any dream to define homotopy between maps with multiple metric spaces?
Yeah, that's a good question. A couple of people have been working on that, including Yoshinaga. In fact, there's a sense in which when you go down that road, you start to conclude that for two parallel maps of metric spaces to be homotopic is for them to be equal on their inner boundary. I know that doesn't sound like the definition of homotopy, but there's a sense in which it feels like when you get into it.
Thank you.
There are two questions, but I don't know your names, I'm sorry.
So two smaller questions. The first smaller question is, you showed some sample computation here, but the sample computation is parameterized by a real variable. Is this, I mean, you can teach an undergraduate or better a computer to compute classical homology. Could you hypothetically do something to like really do computations?
Yeah. So certainly people have programmed computers to calculate magnitude homology for graphs. Simon, do you know if it's been done for arbitrary metric spaces?
No.
You don't know?
I'm not aware of it having been done.
Okay, but that wouldn't be such a big deal. I mean, certainly people talk about finite metric spaces. Of course, anything infinite becomes another question.
Sorry, for finite metric spaces, probably still no. Yeah, I mean,
right. Okay, I guess that answers that.
Yeah, sure. So thanks for this talk. First off, it was really interesting, very clear. We saw earlier on Wednesday a notion of enrichment, which was parameterized in composition that Eugenia talked about. Is there any way to see a generalized notion of magnitude homology to a parameterized enriched category? And if so, what is the topological invariant of that categories?
Yeah, right. I'm afraid I just don't know.
Sure.
Yeah. Thanks.
Eugenia, please.
Thanks for your talk. I would like to hear you say why it's called magnitude homology, although I would also say I downloaded your slides and I saw them.
Right, okay, thank you. Right. Okay, so I'll say this quickly. So there's a numerical invariant of enriched categories that many of you have heard me talk about called magnitude. And the idea of magnitude homology when Simon Richard Hepworth introduced it was to categorify magnitude, at least in the case of graphs. And it's been shown that it does indeed categorify magnitude in the sense that the Euler characteristic of this homology theory is magnitude, in at least two interesting cases. Well, one subsumes the other. However, there's something odd that happens. So magnitude of infinite metric spaces, like things like disks and so on, is super interesting. So for example, if you have a compact subset of Rn, you know its magnitude and also the magnitude of all its rescaled brothers and sisters, then you can extract things like dimension and volume and surface area. There's a lot of analytic work that's gone into this. And in particular, that means, very much in particular, that different convex sets have different magnitude, and wildly so, because they have different dimensions and so on. However, I've already told you they all have trivial magnitude homology, so something is wrong in the foundations of magnitude homology. And a major question, I would say the major question, is to try to refine, we're missing some idea. We have this decategorification for finite spaces, but not for arbitrary spaces. So the definition should be tweaked or refined or rethought out so that we do have this categorification. Thank you.
Are there more questions? Yeah, please.
Thanks for the wonderful talk. The core notion seemed definable for sort of arbitrary metric spaces, but at what point does the topology of Euclidean space come into the theory?
Right. Well, so the core notion is definable if you know if you've decided what it means to be a convex subset of a metric space. And there are, as I said, there are various inequivalent definitions of that. It's not so much a topology, just you end up doing stuff where you want to take like convex combinations, 1/3 x plus 2/3 y and so on to get stuff done. So it's entirely possible we've missed something, but we retreated to that at some stage.
So ordinary homology tells you when you've got holes of various dimensions, so when they exist. So you have a homology that's indexed by a real number.
Yeah.
So at some number this switches from 0 to 1 or whatever. So is that saying the size of the hole? That number?
It's a slightly more delicate relationship. So you have to think about both the parameters, the n and the l. So if you look at that formula again, you can see the l and the n are both appearing.
Right. So the size of the hole of that dimension.
Yeah.
That's what it says.
Yeah. Yeah. So that int is running over all l's and n's.
So are there, Emily?
So I was surprised by the second equivalent condition in your theorem, that it's equivalent to have, so in the presence of these maps, having any agreement on magnitude homology means you have agreement on all magnitude homology.
Yeah.
Can you say anything about why that would be true?
Yeah, but I think Maria Manuel might start looking uncomfortable if I come up with a short way of answering that, so I think I'll just let's talk about that afterwards. I mean, remember this, this is not quite the usual definition of isomorphism in homology. It's much tighter.
Yes, exactly, I know, but still.
So there's kind of two lines of what happens when you go to infinite dimensions. You take an arbitrary Hilbert space. The triangle inequality, if it's equality, you will get the similar kind of things that the point will be in the middle, and then somewhere in the middle. And the other thing is that in Riemannian manifolds you have notions of metric, and you have the curvature, and over the interplay between curvature and.
Okay, so quick answer. So first of all, we needed some stuff that doesn't solve in infinite dimensions. If you have two isometric subsets of Rn, you can extend that to an isometry of the self-isometry of the whole of Rn and moves one to the other. That's not true in infinite dimensions. As far as curvature, so there's a lot. If you look in this bibliography, there's and search the word curvature in there, you'll find some stuff about magnitude homology and curvature that relating.
I'm sure nobody here wants the CT to end, but I will take just a few more questions. So, yeah.
So, thanks for the talk. A very naive question. Is there some relative version of magnitude homology?
That's a good question. I don't know. That's, yeah.
So, homological data analysis.
Can you speak louder?
Is there any relationship with persistent homology?
Funny you ask. So these are both homology theories of metric spaces. They both involve real scalar parameters. You think of one as being a reciprocal of the other. And so it's a question that can be asked, and two different studies of this were made, one by Nina Rosser, one by Simon Cho. Nina Rosser introduced something she called blurred magnitude homology, which is intended to kind of interpolate between the two notions. The short answer is that they capture quite different information. So, but it's the question, although it's received some answers, I think the story is far from complete.
So I think it's
Sorry.
last
I'm so
one.
sorry. If you don't want to say, but I was also just wondering quickly if there's some sort of model structure that is induced by magnitude homology in metric spaces.
I have no idea.
So it's about time to thank the speaker and all those that made questions. I think we had to join an applause for all the speakers at DCT, but this won't be the end. So let's applaud them and then we'll continue.
Anyone who's organised even a small conference knows how much work and stress it is. anyone who's organised a large conference knows how non-linearly things scale. And indeed how much work it becomes when the number of participants exceeds what you were expecting. And I know that the local organiser and the scientific committee have done a huge amount of work for this, and that it did exceed expectations. I believe this is the largest CT there's ever been. I know the scientific committee, I know that every one of them read every submission, which is just an inconceivable amount of work. It's incredible how much they've done. So really, it's clear it's been a very, very major production for all concerned. So I'm sure we're all extremely grateful to the scientific committee, to the local organisers, both the ones who've been more visible this week and the ones who've been less visible this week, the cleaners, janitors, caterers, technical staff, all the people we don't see so much. And so it's really been incredible. And so let's give them an enormous round of applause.